There is probably a deck of cards somewhere in your home. Shuffle it once, and you are holding an arrangement of 52 pieces of paper that has almost certainly never existed before in human history. The possible orderings number about 8, followed by 67 zeros, roughly the count of atoms in our entire galaxy. Physicists use that ordinary deck to explain why time moves forward, why stars burn out, and how the universe ends. But here is what almost nobody tells you. The scientists who study the ending of everything have been losing ground for a century. In 1998, one measurement overturned every textbook. In 2025, the sharpest map of the cosmos ever drawn suggested that the force deciding our fate is changing in ways no theory predicted, and endings declared dead began climbing back onto the table. Right now, physics cannot tell you whether everything ends in a tearing, a collapse, an endless fade, or whether an ending is even something the universe can do. So what will reality look like at the end of the universe? By the end of tonight, you will understand exactly why nobody knows, and why that is the most honest answer in science. Settle in, hit subscribe if you're new here, because by the end of this, the word ending will never mean the same thing again. Now, let's gently fall into this. Part 1. The question that looked answerable. The end of the universe used to be a solved problem. That sounds strange to say out loud, but for most of a century, the people who studied the fate of everything genuinely believed the answer was sitting in a filing cabinet, waiting on one final measurement. The question had exactly two possible answers. The mathematics behind both was clean, and all anyone had to do was count carefully enough. This is the story of how that certainty was taken apart, piece by piece, by the very instruments that were built to confirm it. And the strangest part of the story is that the taking apart never stopped. It begins in 1922, in Petrograd, with a young Russian mathematician named Alexander Friedman. Friedman had spent the war calculating bombing tables from the open cockpit of an aircraft, and he brought that same practical fearlessness to Einstein's brand new theory of general relativity. Working through the equations, he found something nobody wanted to find, including Einstein himself. A universe filled with matter cannot stand still. The equations refuse to allow it. Space as a whole must either be expanding or contracting. The way a ball thrown into the air must either be rising or falling. It is simply not permitted to hang there. Einstein's first response was to publish a short note claiming Friedman had made a calculation error. He had not, and to his credit, Einstein published a retraction admitting the young man's results were correct. But Friedman never got to enjoy the vindication. He died of typhoid in 1925, at 37 years old, 4 years before the American astronomer Edwin Hubble showed that distant galaxies really are receding from us in every direction. The universe was expanding exactly as the mathematics had insisted it must. And from that moment on, the fate of the universe stopped being a philosopher's question and became something you could, in principle, calculate. Here is how the calculation was supposed to work, and it is worth feeling how reasonable it is. An expanding universe is a contest between two forces. On one side, the outward momentum of the expansion itself, inherited from the beginning. On the other side, gravity, the collective inward pull of every galaxy, every star, every atom of matter, all of it gently breaking the expansion, trying to haul everything back together. The outcome of that contest depends on a single quantity, the average density of the universe. How much stuff is there per cubic meter of space? Physicists even computed the exact tipping point, which they called the critical density. It comes out to roughly 9 times 10 to the minus 27 kilograms in every cubic meter, the equivalent of about 5 or 6 hydrogen atoms in a volume the size of a large moving box. To put that number in perspective, it is like taking a single grain of sand, grinding it into dust, and scattering it evenly through a volume larger than the entire Earth. That is the knife edge on which everything was thought to balance. If the real universe is denser than that, gravity eventually wins. The expansion slows, stops, and reverses, and tens of billions of years from now, everything comes crashing back together in a hot, dense finale that physicists came to call the Big Crunch. The Big Bang played in reverse. If the real universe is thinner than that, gravity loses. The expansion never quite stops. The galaxies drift apart forever, and the universe simply coasts outward into an ever colder, ever emptier future. Crunch or coast, fire or fade. 2 boxes, and reality had to tick one of them. By the middle of the 20th century, textbooks presented the fate of the universe in almost administrative language. Count the atoms, weigh the galaxies, compare the number to the critical density, and read off the ending. It was treated as an accounting problem, and everyone assumed the account would eventually be settled. One man took the accounting further than anyone, and he deserves a moment here, because his story carries the first quiet warning. Richard Tolman was a Caltech physicist with 2 parallel lives. When his country went to war, he was pulled into its most serious scientific machinery, the Chemical Warfare Service in the First World War, and years later, a senior advisory role in the Manhattan Project, helping oversee the building of the atomic bomb. But in the calmer years between, Tolman devoted himself to a subject most physicists then considered a beautiful dead end: Einstein's general relativity, applied to the universe as a whole. In 1934, he published a book that quietly became a cornerstone of cosmology, and in it he asked a wonderful question. If the universe can expand and then recollapse, could it bounce? Could the crunch at the end ignite a new bang, and that universe crunch and bounce again, forever? An eternal, cyclic universe. No true beginning, no true ending, just an endless breathing, in and out. Versions of that idea are far older than physics. Hindu and Buddhist cosmology imagined time as a wheel turning through immense repeating ages. Tolman showed that, remarkably, nothing in the laws of thermodynamics strictly forbids a bouncing universe. The old wheel of time could be written in the language of Einstein's equations. But then Tolman found the catch, and the catch is the first crack in this whole story. Disorder survives the bounce. Every cycle of the universe generates entropy, waste heat, disorder, the used-up quality of energy that has already done its work, and that entropy does not reset when the universe collapses and rebounds. It carries over, like interest on a debt, and a universe carrying more entropy bounces bigger. Each cycle comes out larger and longer than the one before it, which means the cycles are not a perfect circle after all. They are a spiral. Trace the spiral backward, and the cycles shrink and shrink and shrink toward a beginning you were trying to avoid. Trace it forward, and the wheel slowly unwinds. Even the tidiest picture of an eternal universe, the moment someone examined it with real care, refused to close its own loop. It is worth pausing on what Tolman had actually done, because it set a pattern that will repeat through this entire story. He took the most comforting answer available: everything returns, nothing truly ends, and studied it more carefully than anyone before him. And the answer came back stranger and less settled than when he started. The study itself was flawless. The understanding still went down. Hold on to that feeling, because we are going to watch it happen again and again, with better instruments and higher stakes, all the way to the present day. Still, in those mid-century decades, the mood remained confident. The fate of the universe was a two-answer question, and every year the telescopes grew, the surveys deepened, and the count of the universe's matter sharpened. And underneath both possible answers sat one assumption so obvious that almost nobody thought to question it. Whatever the final tally said, crunch or coast, the expansion of the universe had to be slowing down. It could not be otherwise. Gravity pulls. Gravity has been breaking the expansion since the first moment. The only question worth asking was how hard the brakes were pressing. Both endings assumed it. Every textbook assumed it. It was not even considered an assumption. It was considered common sense, the one fixed point in the whole discussion. So the plan for settling the fate of the universe as the 1990s opened was simple and beautiful. Measure the braking. Measure precisely how much the cosmic expansion has slowed over the last several billion years, and the ending falls out of the arithmetic. Two teams of astronomers set out to do exactly that, racing each other to be first. "We are not waiting for the end," one of them might have said. "We are simply waiting for the final digit of a number we already mostly know." What they found instead would tear up the two-answer question forever. Because when the measurements finally came back, the universe was not slowing down at all. Part 2. The night the universe sped up. To measure how hard the universe is braking, you need to compare the expansion rate today with the expansion rate billions of years ago. And to do that, you need to see billions of years into the past, which means you need something almost absurdly bright, and you need to know exactly how bright it truly is. The astronomers of the 1990s found their tool in the most violent, ordinary event the universe produces: the complete destruction of a dead star. A white dwarf is the leftover core of a star like our Sun, a sphere of carbon and oxygen about the size of the Earth, so compressed that a single teaspoon of it would weigh several tons. On its own, a white dwarf just sits there, cooling quietly for eternity. But give it a companion star, close enough to feed on, and something remarkable becomes possible. The white dwarf pulls a thin stream of gas off its neighbor, growing heavier, century after century, until it approaches a very specific threshold, about 1.4 times the mass of our Sun. That number is called the Chandrasekhar limit, and it is the most important weight limit in astronomy. At that mass, the dwarf can no longer support itself. In a matter of seconds, a runaway wave of nuclear fusion tears through the entire star, and the whole thing detonates. Nothing is left behind. The explosion is called a Type 1a supernova, and at its peak, it shines with the light of roughly 5 billion suns, briefly outshining the combined glow of every other star in its home galaxy. Here is why that matters for measuring the universe. Because the bomb always goes off at the same weight, the explosion always releases close to the same amount of light. Astronomers call an object like that a standard candle. If every candle burns with the same true brightness, then a candle that looks dim must be far away, and one that looks bright must be near, and the dimness tells you the distance with real precision. In the early 1990s, astronomers sharpened the tool even further, discovering that the small remaining differences between these explosions could be corrected by watching how quickly each one fades. With that correction, a Type 1a supernova becomes a distance marker, readable from more than halfway across the visible universe. Scatter enough of them across cosmic history, and you can reconstruct how fast the universe was expanding in every era. You can measure the braking. Two rival teams went hunting. One, the Supernova Cosmology Project, was led by Saul Perlmutter at Berkeley. The other, the High Z Supernova Search Team, was led by Brian Schmidt in Australia, with a young astronomer named Adam Rees doing much of the critical analysis. The rivalry was real. They competed for telescope time, raced each other to publication, and checked each other's work with the enthusiasm of people who would very much enjoy finding the other team's mistake. Both teams expected the same result. Distant supernovae should look slightly brighter than a naive calculation suggests, because a decelerating universe would not have carried them as far away as a coasting one. The measurement was supposed to reveal how much brighter, and therefore how strong the braking was, and therefore how the universe ends. It is the autumn of 1997, and in an office at the Space Telescope Science Institute in Baltimore, Adam Rees is running the numbers again. On the screen in front of him are light curves. the rising and falling brightness of exploding stars in galaxies so distant their light left home when the Earth was half its current age. He feeds them through the analysis, and the software returns a value for the mass of the universe, and the value is negative. He checks the calibration. He checks the dust corrections. He reruns everything from the beginning, because a universe with negative mass is not a discovery. It is a mistake. Somewhere, it has to be a mistake. It refuses to be a mistake. The supernovae are simply too faint. They are sitting significantly farther away than the strongest possible braking allows, farther even than zero braking allows. The equations, offered no other escape, are trying to describe a universe that is being pushed. He is, at this moment, one of a handful of human beings who has seen this, and he does not particularly want to be. There is a long stretch of checking and rechecking, of carefully worded emails, of wondering how a young scientist announces something like this without ending his career. Across the country, the rival team is quietly staring at the same impossibility in their own data, each group half hoping the other will stand up first and take the fall. The supernovae were between roughly 10 and 25% fainter than expected, not brighter, as deceleration required, fainter. The expansion of the universe was not slowing down, it was speeding up. Brian Schmidt later described his team's reaction as running somewhere between amazement and horror, and both words were earned. Deceleration was not one hypothesis among many, it was the shared flaw under every model of the universe's future. Gravity pulls. Everyone knew gravity pulls. And yet here were dozens of dead stars, scattered across billions of light years, all quietly reporting that something out there pushes harder. What happened next is, in its way, as remarkable as the discovery itself. Science is often slow to accept a shocking result, and it should be. But this one came from two competing teams, using independent data, independent software, and independent chains of reasoning. Teams whose fondest professional wish was to catch the other in an error. When both walked into the same conference in early 1998, carrying the same impossible answer, the community's resistance collapsed with astonishing speed. Within months, the accelerating universe went from heresy to headline. Science magazine crowned it the breakthrough of the year for 1998, and 13 years later, in 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics. The skeptics, to be fair, did not surrender without a fight, and the fight made the results stronger. Perhaps, some argued, the distant supernovae were not farther away at all. Perhaps some grey fog of intergalactic dust was dimming their light, mimicking distance. Or perhaps supernovae in the young universe were simply built differently, born from stars with a different chemistry, and exploded a little less brightly than their modern cousins. These were serious objections, and the teams spent years answering them. Dust tends to redden starlight as well as dim it, and the distant supernovae were not reddened in the way real dust requires. And the shapes of their light curves, the precise rhythm of brightening and fading, matched nearby explosions in every detail that could be checked. Then came the decisive witness. If the universe truly switched from slowing down to speeding up partway through its history, then supernovae from the earliest epochs, before the switch, should look slightly brighter than expected, not fainter. In 2001, the Hubble Space Telescope delivered exactly that, an ancient supernova, its light more than 10 billion years old, sitting on the bright side of the ledger, precisely where a universe that once decelerated and then began accelerating says it should be. The dimming was not dust, and it was not chemistry. It was the universe, changing gears. Take a moment to feel what died that night, because it is the hinge of this entire story. The two-answer question died. Crunch or coast? Both options assumed the expansion was slowing, and it was not, so the tidy accounting problem that generations of physicists had prepared for simply no longer existed. The textbooks were not slightly wrong, in need of a decimal place correction. They were structurally wrong. The contest between expansion and gravity turned out to have a third contestant that nobody had entered into the race, invisible, unnamed, and winning. And consider what it takes to win that race. Gravity is the collective pull of everything. Every galaxy, every star, every black hole, every scrap of gas and dust in the observable universe, hundreds of billions of galaxies, all tugging inward at once. Whatever was accelerating the expansion was overpowering all of it combined, and doing so not in some exotic corner of space, but everywhere, in every direction astronomers looked, across billions of years of cosmic history. Overnight, the deepest question in cosmology changed shape. It was no longer, how much does the universe weigh? It was, what in the world is pushing? Because here is the uncomfortable arithmetic that was already dawning on physicists in the spring of 1998. For something to outmuscle the gravity of everything visible, it cannot be a trace ingredient, a minor correction at the edge of the equations. It has to be the main ingredient. Whatever this push was, the numbers were about to show that it makes up most of the universe, most of everything that exists. And that raises a question with an answer nobody, to this day, has been able to give. If this thing is most of the universe, then what is it? Part 3. We named our ignorance. Science has a quiet tradition for moments like this. When physicists discover something enormous and have no idea what it is, they give it a name, and the name buys them time. In 1998, the cosmologist Michael Turner coined the name for the push, dark energy. It is worth being clear-eyed about what that name is. It is not a description, it is not a theory, it is a placeholder, a label pasted onto a locked box. The word dark, in cosmology, has become an honest little flag that means we cannot see it and we do not understand it. It had already been used once before, for dark matter, the invisible extra mass that holds galaxies together, which remains unidentified after nearly a century. Dark energy was a second name for a second, entirely different ignorance. Naming it was still progress, in the way that drawing a border around a blank region of a map is progress. But it is a strange kind of progress, and it should feel strange. The discovery of the decade was, in effect, the discovery of how much had not been discovered. Then came the census, and the census is where the ground really shifts under you. Over the following 2 decades, measurements of the afterglow of the Big Bang, the cosmic microwave background, mapped in exquisite detail by satellites, most recently the Planck mission, allowed cosmologists to weigh the ingredients of the universe against each other. The recipe they read out is now one of the most precisely measured results in all of science, and it says this: dark energy makes up about 68% of everything, dark matter makes up about 27%, and ordinary matter, every atom in existence, every galaxy, every star, every planet, every ocean, every person, everything that has ever been seen, touched, or detected by any instrument in human history, comes to just under 5%. Sit with that for a moment, because it is easy to let it slide past. 95% of the universe is made of 2 substances that have never been produced in a laboratory, never been captured in a detector, and never been identified. The part of reality we actually understand, the part physics spent 4 centuries mastering, from falling apples to atomic clocks, is a rounding error. And the component that holds the controlling share, the majority owner of the cosmos, is the one discovered last and understood least. The fate of the universe, which once hung on counting hydrogen atoms, now hangs entirely on the behavior of the 68% we cannot name. What can be said about dark energy from the way it behaves? A few things, and each one deepens the puzzle rather than settling it. It does not appear to clump. Matter gathers into stars, galaxies, filaments, but dark energy stays perfectly smooth, the same in every direction, the same everywhere. It appears to belong to space itself, as if emptiness came with a built-in energy content, a faint pressure woven into every cubic meter of vacuum. And strangest of all, it does not seem to dilute. Spread matter through a growing volume, and it thins out. That is common sense, and matter obeys it. Dark energy, as far as anyone can measure, does not. Double the amount of space, and you appear to get double the dark energy, at full strength, as though the universe manufactures more of it simply by growing. That is why its victory over gravity was inevitable. Matter's pull weakens as space expands and matter spreads thin. A push that lives in space itself never weakens at all. For the first several billion years, matter was concentrated enough to dominate, and the expansion slowed. Then the thinning crossed a line, roughly 5 or 6 billion years ago, and the push took over. The universe has been accelerating ever since. We happen to live just after the handover. Here is a way to hold all of this that you can take outside with you tonight. Stand under a clear sky and look up. Every point of light you can see, every star, every planet, the faint band of the Milky Way, belongs to the 5%. So does the darkness between them, in a sense. Because even the gas and dust hiding there is ordinary matter, the familiar kind, the kind that makes atoms and chemistry and you. Now understand that the actual majority of the universe is also up there, and also down here, threaded through the room you are sitting in, through the space inside your own body, utterly beyond your senses. It does not glow. It does not reflect. It does not brush against a single nerve. The night sky, which feels like the universe showing itself to you, is closer to the opposite. It is the thin, luminous skin stretched over a body of darkness. Nothing about the sky looks different once you know this. And yet, if you let the thought settle, everything about it feels different, quieter, heavier, more secretive. Astronomers sometimes say we study the foam on the wave. The wave itself, the 68% that decides where everything is going, has never once let itself be seen. There is one obvious candidate for what such an energy could be, and its history is one of the great ironies in physics. In 1917, Einstein himself added a term to his equations called the cosmological constant, a fixed energy of empty space, because he wanted his equations to permit a static universe, and they otherwise refused. When expansion was discovered, he reportedly regarded the term as a great blunder, and it was quietly dropped. 80 years later, the supernova data dragged it back out of the wastebasket. A constant energy of the vacuum is precisely the kind of thing that would never dilute and would push exactly the way the data shows. On paper, it fits beautifully. But when quantum theory, our most precise theory of nature, is asked to calculate how much energy empty space should contain, it returns an answer that is too large by a factor of roughly 10 to the power of 120. Not 100 times too big, not a million, a 1 followed by 120 zeros. It is routinely called the worst theoretical prediction in the history of physics, and it means the one explanation that matches the data is also the one explanation our deepest theory gets more wrong than any number it has ever produced. Notice the shape of what has happened to our question, because the shape is the story. In 1930, the end of the universe was a one-number problem. Measure the density, read off the fate. By 2000, it had become a one-substance problem. Identify dark energy, and then read off the fate. That sounds like the same kind of problem, but it is not. A number can be measured. A substance that interacts with nothing, casts no shadow, and lives identically in every cubic meter of emptiness, offers almost nothing to grab. The question had not been answered. It had been relocated, moved into the largest and least accessible territory in all of physics. And yet, if you had asked a cosmologist around the year 2000 whether the situation was hopeless, they would have said something genuinely reasonable. No, they would have said, we do not need to know what dark energy is to know what it will do. We only need to know one thing about it, how its strength responds as space keeps growing. Does it hold perfectly steady forever? Does it slowly tire? Or, the option nobody wanted to say out loud, does it grow? That single behavior, they realized, could be captured in a single measurable number. Measure it, and the ending falls out of the arithmetic. No identification required. The fate of the universe had been compressed, once again, into one number. And this time, physicists were sure the number would cooperate. It is one of the most quietly consequential numbers in all of science, and the story of trying to pin it down is the story of the next part. Because the universe, it turns out, had hidden the answer directly on top of a knife edge. Part 4. The number that refuses to choose. The number is called W, and it deserves to be famous, because no other number in physics carries this much weight. In plain terms, W describes dark energy's personality. It measures the relationship between dark energy's pressure, the push it exerts, and its density, how much of it sits in each cubic meter of space. What makes it the fate-deciding dial is a single question hidden inside it. As space keeps growing, what happens to the strength of the push? Everything, and this is not an exaggeration, everything about how the universe ends comes down to which side of one particular value this number falls on. That value is -1, and physicists call the line it draws the phantom divide. Suppose W equals exactly -1. Then dark energy is Einstein's cosmological constant, come home at last, a fixed, unchanging property of empty space. Every new cubic meter of universe arrives with the same small allotment of push, forever. The expansion accelerates gently and eternally. Galaxies drift apart faster and faster, and the universe glides into the long fade, an ending physicists call heat death, which we will walk through properly later tonight. It is the calmest of the endings, if calm is the right word for eternity. Suppose instead that W sits a little above -1, somewhere between -1 and about -1/3. Then dark energy is not a constant of nature, but a field, a dynamic ingredient of the universe. Physicists call this family quintessence, borrowing Aristotle's word for the fifth element. A quintessence field can tire. Its push slowly wanes as the eons pass. The acceleration softens, and the universe expands forever at an ever gentler pace. This ending resembles the long fade, but with the pressure easing rather than holding, the difference between a wind that blows forever and a wind that gradually dies. And then there is the third possibility, the one that sounds like it should not be allowed. Suppose W falls below -1, even slightly, even by a hair. Robert Caldwell, the physicist who worked out this scenario in 2002, gave it a name that has stuck: phantom energy. Below the divide, dark energy's density does not hold steady as space grows, and it does not tire. It grows. More space means more push per cubic meter, which drives faster expansion, which creates space faster, which strengthens the push. The universe's accelerator pedal is wired to its own speedometer. Run that feedback forward, and it does not merely continue, it runs away. And the mathematics delivers something no other ending contains: a finale at a specific, finite date. Caldwell and his colleagues published the schedule in 2003 in a paper bluntly subtitled Phantom Energy and Cosmic Doomsday, and it reads like a demolition plan for reality. As the runaway builds, the expansion of space begins to compete with the forces that hold structures together, and structures lose in order of size. First, roughly 1 billion years before the end, the great clusters of galaxies are pulled apart, their members scattered. Some 60 million years before the end, our own galaxy's stars are peeled away from each other as the stretching overwhelms the galaxy's gravity. 3 months before the end, planets are stripped from their suns. Half an hour before the end, planets themselves come apart, the ground literally rising as the space beneath it swells. And in the last unimaginable fraction of a second, around 10 to the minus 19 seconds before the finale. Atoms themselves are torn open, nuclei shredded, and then the runaway reaches infinity, and the equations of general relativity simply stop. Space and time end in what physicists call a singularity, not darkness, not emptiness, an edge, beyond which the mathematics has nothing further to say. This is the Big Rip, and for their illustrative example, W equal to minus 1.5, the authors calculated the whole show would conclude roughly 22 billion years from now. The universe is currently 13.8 billion years old. If that particular number were right, existence would already be almost 40% finished. For completeness, there is even a fourth ending on the menu, one that has nothing to do with W at all, the possibility, taken seriously in particle physics, that empty space itself is not in its most stable configuration and could one day decay, rewriting the laws of physics outward at the speed of light. It is speculative, it is unconfirmed, and we will leave it as a single unsettling sentence. The point of mentioning it is only this. The menu of endings has a way of growing every time someone looks closely at anything. So there is the situation. Above -1, a universe that gently tires. At -1, a universe that fades forever. Below -1, a universe that fades forever. Below -1, a universe that fades forever. Below -1, a universe that fades forever. Three futures that could not be more different. Infinite versus finite. Dissolution versus annihilation. Separated by a boundary of zero width. And so, for the past quarter century, that is what cosmology has bent much of its worldwide effort toward doing, combining the supernovae with the microwave background, with maps of millions of galaxies, with the bending of light by cosmic structure, stacking survey upon survey, decade upon decade, precisely because everything depends on this one number. Here is what all of that effort has returned. The Planck satellite's analysis, combined with the supernova and galaxy data, found W equal to -1.03, plus or minus 0.03. Other combinations of datasets land at values like -1.01, with error bars of similar size. Read those numbers slowly, because they are a masterpiece of cosmic ambiguity. -1.03, plus or minus 0.03. The measurement brackets the divide. It is consistent with exactly -1. It is consistent with slightly above -1. It is consistent with slightly below -1. Which is to say, the long fade fits the data, the gentle tiring fits the data, and the big rip fits the data. Three qualitatively different fates of everything that exists, all sitting comfortably inside a single error bar, a few percent wide. Humanity has measured the number that decides the ending of the universe to 2 decimal places, an astonishing achievement by any standard, and the 2 decimal places refuse to choose. It is worth understanding why this measurement is so brutally hard, because the difficulty is not carelessness, it is the nature of the quarry. No instrument can detect dark energy directly. You can only watch what it does to the universe, and what it does unfolds over billions of years. So cosmologists triangulate. The supernovae trace how distances have stretched across cosmic history. The microwave background provides a snapshot of the universe at its beginning, anchoring the starting conditions, and the large-scale arrangement of galaxies records how structure grew, or was prevented from growing, under dark energy's influence in between. Each method alone carries its own blind spots and its own systematic errors. Only where all three overlap does a trustworthy value of W emerge. It is like determining the weight of a sealed chest you may never open, using only the depth of the wagon ruts it left across 3 different roads. That the answer has been squeezed to within a few percent is a triumph. But a few percent, in this one uniquely cruel corner of physics, is precisely not enough, because the entire meaning of the answer changes across a line thinner than any error bar humanity has yet produced. Imagine a doctor telling you a test result came back as -1.03, plus or minus 0.03, where anything above -1 means you will live forever, and anything below it means a scheduled catastrophe. The precision would be admirable. It would also be no comfort at all. And there is a deeper strangeness here, one that keeps cosmologists up at night for reasons beyond the obvious. Of all the values Dewey could have taken, any number on an infinite line, the measured value sits exactly on the one boundary where the nature of the answer flips. There is no known reason for that. If dark energy is truly Einstein's constant, the coincidence is explained, but then we are back to the prediction that quantum theory botches by 120 orders of magnitude. If dark energy is not the constant, then the true value sits some tiny distance from -1, on one side or the other, and 28 years of ever-sharpening measurement have been unable to resolve which side. The universe, it seems, has parked its most consequential secret directly on top of a knife edge, at the precise angle from which we cannot see which way it leans. By the 2010s, everyone in the field agreed on the next move, and it had the reassuring shape of every previous next move. Build a sharper instrument. Map not thousands of galaxies, but tens of millions. Shrink the error bar until the knife edge finally resolves, and read off, at long last, the fate of the universe. The instrument was built. It is one of the most remarkable machines on Earth, and it worked better than anyone dared hope. What it found is the reason this video exists. Part 5. The Sharper Map. On a mountaintop in the Arizona desert, inside the dome of the 4-meter Mayall telescope on Kitt Peak, sits a machine that would have sounded like science fiction to the supernova hunters of the 90s. It is called the Dark Energy Spectroscopic Instrument, DESI for short, and its heart is a disc holding 5,000 robots, each one a slender fiber optic positioner about the width of a pencil. When the telescope swings toward a patch of sky, all 5,000 robots pivot in unison, a quiet mechanical choreography lasting seconds, until each fiber points at one pre-selected galaxy. Then the sky's light pours down 5,000 threads at once, each thread carrying the complete spectrum of a single galaxy, its colors, its chemistry, and crucially, its distance. Every 20 minutes or so, the robots reshuffle and drink in 5,000 more. Night after night, year after year, DESI has been performing the largest act of cartography in human history, a three-dimensional map of the universe, tens of millions of galaxies strong. The map matters because of what is hidden in the spacing of the galaxies. In its first few 100,000 years, the universe was a hot, glowing fog, and sound waves, actual pressure waves, ripples in that primordial plasma, rolled through it. When the fog cleared, those ripples froze in place, leaving a faint preference in how matter clumped. Galaxy pairs today are very slightly more likely to sit about 490 million light-years apart than at similar distances on either side. That frozen ripple is called a baryon acoustic oscillation, and it functions as a ruler of known length stamped across the entire cosmos, at every epoch of its history. The supernovae gave cosmology standard candles. The ripples give it a standard ruler. Measure how large the ruler appears at different cosmic ages, and you reconstruct the expansion history of the universe with a precision candles alone could never reach. And from the expansion history, you read the behavior of dark energy. This was the instrument that was going to close the case. Shrink the error bar on W, resolve the knife edge, and finally write the last chapter of the textbook. In April of 2024, the DESI team released its first year of results, built on about 6 million galaxies and quasars, already the largest map ever made. And the map contained a hint that made cosmologists around the world sit up straight. The data showed a mild preference, suggestive, not conclusive, for a dark energy that is not constant at all, a dark energy that changes with time. In March of 2025, the second release arrived, now built on nearly 15 million galaxies, And the hint had not gone away. It had grown. Combined with the microwave background and the largest supernova catalogues, the preference for evolving dark energy reached, in the strongest combination, 4.2 sigma, statistical language meaning that if dark energy were truly constant, data this misleading would arise by chance, roughly once in 50,000 tries. That is not yet the 5 sigma standard physics demands before declaring a discovery. 5 sigma means odds of about 1 in 3.5 million, and every careful scientist involved says so plainly. But it is far past the level anyone can ignore. And the shape of what the data suggests is stranger than almost anything theorists had on the menu. It is not simply that W sits a little off from -1. The evidence concentrates in something more unsettling, the change in W over time. Averaged across cosmic history, dark energy still masquerades as Einstein's constant. That is the very coincidence that made it look settled for 2 decades. But split the history into then and now, and the data prefers a story in which dark energy was stronger than the constant in the distant past, below the phantom divide, in the forbidden-feeling territory of phantom energy, and has since been weakening, crossing the divide, and continuing to fade today. One commentary in a major journal captured the mood in 4 words: the inconstant cosmological constant. Stop and appreciate how deeply strange that trajectory is. For a quarter century, the fear was that W might sit quietly on the wrong side of a line. Nobody ordered a dark energy that wanders across the line. And the crossing itself is a theoretical scandal, because the simplest kinds of dark energy field, the well-behaved quintessence models, provably cannot cross the phantom divide without becoming unstable. If the crossing is real, then dark energy is not Einstein's constant, and it is not the simplest field, and it is not the simple phantom. It is something else, something with internal workings nobody has correctly guessed, and the crown jewel measurement of modern cosmology has, in effect, returned the answer, none of the above. Now follow the implications for the ending, because they bend in a direction nobody saw coming. A dark energy that is weakening opens a door that 1998 was thought to have nailed shut. If the fading continues, and this is a model-dependent extrapolation, stated here, with all appropriate caution, the push could weaken to 0 and then turn negative, becoming a pull. Space itself would begin to contract. Galaxies that spent eternity fleeing one another would slow, turn, and fall back. The Big Crunch, the ending that spent a quarter century in the graveyard of discarded ideas, has been quietly exhumed and returned to the table. One paper by physicists at Princeton and elsewhere, published in 2022, explored descending dark energy scenarios, consistent with current data, in which the expansion could end and reverse, on timescales that are, cosmically speaking, startlingly short, in the more dramatic toy models, within tens of billions of years or less. Those particular numbers should be held loosely. The models are illustrations, not predictions. The point is the door. It was closed. It is open. And now, the caveat, and listen closely, because in this story the caveat is not a footnote, the caveat is the discovery. The strength of DESI's evidence depends on which catalogue of supernovae you combine it with. Pair the galaxy map with one major supernova compilation, and the significance sits near 2.8 sigma. Interesting. Inconclusive. Pair it with a different compilation, assembled by a different team with different calibrations, and it rises past 4. Same universe, same map. Different supernova bookkeeping, different verdict. Meanwhile, other researchers have found mild internal tensions among the microwave background, the galaxy ruler, and the supernovae themselves, the 3 roads that are supposed to converge on one answer, showing faint signs of disagreeing with each other. Some argue part of the evolving energy signal could be an artifact of supernova calibration. Others argue it is robust. The sharpest map of the universe ever drawn cannot, at present, fully agree with itself about what it is seeing. The sharper the map, the stranger the territory. Hold on to that sentence. We will meet it again before the night is over. Because look at the scoreboard across one human lifetime. In 1997, there were 2 possible endings, and confidence. In 1999, there was 1 ending, and a Nobel Prize on the way. After 2002, there were 2 again, balanced on a knife edge. After March of 2025, there are at least 3 live endings: the fade, the rip, and the resurrected crunch. Plus the possibility that dark energy is a shapeshifter, obeying rules nobody has written down. Each step in that sequence was driven by better data. The instruments have never once failed. The measurements have never been sloppier than the generation before. They have always been sharper, and the understanding, measured honestly by the number of futures we cannot rule out, has gone steadily, relentlessly backward. A word of honest calibration about that 4.2 sigma, because physics has been burned before. The history of the field is scattered with 3 sigma effects that swelled, held the community breathless for a year or 2, and then dissolved as more data arrived. Statistical mirages, instrumental quirks, bookkeeping ghosts. Particle physicists in particular tell these stories the way sailors tell storm stories, and it is exactly why the 5 sigma standard exists. So the DESI signal may yet fade, and if it does, dark energy will settle back into being Einstein's constant, and the long fade will resume its place as the default ending. But notice what that outcome would actually mean for our question. It would mean the constant that theory misestimates by 120 orders of magnitude is real and permanent, and the knife-edge coincidence stands unexplained forever. There is no outcome here that restores the old comfort. Either the signal is real, and dark energy is a shapeshifter nobody understands, or the signal is false, and dark energy is a constant nobody can explain. The measurement can still go either way. The understanding, either way, has already taken the hit. More data is coming, and quickly. DESI's full 5-year map, the European Euclid Space Telescope surveying billions of galaxies, new observatories mapping the sky every few nights. Every cosmologist alive wants these machines to settle it. Every cosmologist alive also remembers what happened the last several times a better machine was switched on. You might hope the fix is patience. Keep mapping, keep counting, and surely the knife edge resolves eventually. Perhaps. But the universe has one more twist prepared on this front, and it is crueler than ambiguity. The window in which the question can be answered at all is closing, because the evidence itself is leaving. Part 6. The universe is deleting its evidence. Every question we have asked tonight rests on a quiet assumption that the universe will keep holding still for its portrait, that the data will always be out there, waiting, for as long as it takes us to grow clever enough to read it. In 2007, the cosmologists Lawrence Krauss and Robert Scherer published a calculation that took that assumption outside and quietly dismantled it. Their question sounded innocent, almost playful. What will cosmology look like to astronomers in the far future? The answer turned out to be one of the loneliest results in all of physics. Start with what acceleration actually does to the sky. An accelerating universe has an event horizon, a distance beyond which light launched today will never, ever reach us, because the space in between grows faster than the light can close the gap. That horizon currently sits around 16 to 17 billion light-years away. Any galaxy beyond it has already sent us its last new photon, in the sense that nothing it emits from now on will ever arrive. And here is the number that should stop you. Of all the galaxies inside our observable universe, the full census, hundreds of billions of them, roughly 94% have already crossed that line. If we left tomorrow, traveling at the speed of light, we could never reach them. Their light still trickles in, old light, light from before the door closed, like letters still arriving from a correspondent who has already died. But the connection is severed. Most of the universe is already, in every practical sense, gone. And the door keeps closing. Run the acceleration forward, assuming the constant energy scenario, the calm default, and one by one, Every galaxy beyond our immediate neighborhood is carried over the horizon. In roughly 100 billion to a trillion years, the process completes. The thousands of galaxies whose mutual gravity binds them to us, our local group, dominated by the Milky Way and Andromeda, which will long since have merged into a single sprawling collection of aging stars, will remain, an island exempted from the expansion by its own gravity. Everything else will be over the edge. And it gets worse, because the two great pillars of evidence for the Big Bang itself are also perishable. The cosmic microwave background, that faint afterglow that told us the universe's age and recipe, will be stretched by the expansion to wavelengths longer than any realistic antenna, fainter and fainter, redder and redder, until it is undetectable in principle for any instrument smaller than a galaxy. And the expansion itself becomes unobservable, because there is nothing visible left outside the island to be seen receding. Now stand there, because this is worth experiencing from the inside. It is a night 1 trillion years from now, on some quiet world orbiting a small, patient red star. You step outside and look up. The sky is not empty. It is full of stars, old ones, amber and crimson, the long-lived remnants of the merged island galaxy arching overhead in a single luminous band. It is beautiful, but that band is everything. Beyond it, in every direction, at every wavelength, to the limit of every conceivable instrument, there is nothing. No other galaxies, no faint smudges rewarding a bigger telescope, no glow behind the darkness. The astronomers of this world are brilliant, careful, and honest. They build observatories of stunning power, and the observatories report, decade after decade, the same serene result. The universe is one galaxy, floating motionless in an infinite black stillness, and it appears to be eternal. These astronomers reconstruct their island's history with beautiful precision, but nothing they can ever observe hints that space expands, that there was a beginning, that the darkness was once filled with 100 billion other galaxies streaming away. On this world, the Big Bang is not a discarded theory, it is an undiscoverable one. Let the meaning of that settle. Those future astronomers do everything right, and they arrive at a picture of reality that is fundamentally wrong, not through error, not through arrogance, but because the evidence left before they arrived. Their best science, honestly performed on everything available, will describe a static, eternal, one-galaxy cosmos. Every signature of the truth will have been carried over the horizon, redshifted into silence, deleted by the expansion itself. The universe does not merely evolve, it shreds its own records as it goes. And now, turn that thought around, because it does not only point forward. We are also late arrivals. The universe was already 13.8 billion years old when we started looking, already accelerating, already carrying its outer provinces over the edge. So the uncomfortable question writes itself. What has already been deleted? Are there chapters of cosmic history, entire eras, entire classes of evidence, the very clues that might distinguish one ending from another, that crossed the horizon before any telescope on Earth opened its eye? We have no way to know. That is not rhetoric. It is the precise content of the theorem. Evidence that has left the observable universe leaves no gap labeled missing. The library does not show you the empty shelves. The fate of the universe may hinge on information that no longer exists inside our horizon, and if it does, no instrument, however sharp, will ever recover it. Some of our confusion may not be temporary. Some of it may be permanent, structural, woven into when we happen to be born. Cosmologists have combed the scenario for loopholes, and the search itself is telling. Some have suggested that the island's future astronomers might catch a lucky break, now and then. A close gravitational encounter flings a star out of a galaxy at enormous speed, and such a runaway star, escaping the island entirely, would eventually be picked up by the cosmic expansion and carried away. A single receding lantern that a sufficiently patient civilization might track, and from it, deduce that space itself stretches. It is a real idea, published in earnest, and notice what it amounts to: the entire evidentiary basis of cosmology, reduced to watching one thrown star. Other proposals are more exotic and lean on physics we do not yet possess. The honest summary is that the deletion is thorough, and the workarounds are threads. Krauss and Scherer ended their paper with a sentence that has been quoted ever since, noting that we may live in a very special time, the only era in cosmic history when the universe's true story is actually readable from inside it. Astronomers sometimes rank the great demotions of science. The Earth is not the center. The Sun is one star among billions. Our galaxy is one among hundreds of billions. This result belongs on that list, but inverted and stranger, a promotion nobody wanted. We are not privileged in where we live. We appear to be privileged in when. It is worth pausing here, at the midpoint of our story, to stack up what we have gathered. Slowly, piece by piece, like stones. The expansion of the universe is real, and it is accelerating. That has been checked beyond reasonable doubt. The thing driving it makes up about 68% of everything, and it has never been identified. The one number that would tell us the ending sits balanced on the exact line where the answer flips, and has sat there, unresolved, for 28 years. The sharpest map ever made suggests the thing is changing over time, in a way no leading theory predicted, reviving an ending declared dead a generation ago. And the map's own datasets quietly disagree about how much to trust the signal. And beneath all of it, the window for answering is narrowing, because the universe deletes its evidence as it runs. Every one of those stones was quarried by better instruments than the generation before. That is the pattern, stated in full. The more precisely we studied the end of the universe, the more possible ends there were, and the less certain we became that the question can ever be closed from inside. And yet, suppose we set the measurement troubles aside. Suppose dark energy really is the constant. The knife edge resolves to exactly -1, and the calmest ending, the long fade, the heat death, is the true one. Surely then, the story is finally simple. The universe cools, dims, and settles into stillness, forever. No singularities, no exotic physics, just thermodynamics playing out to its patient conclusion. That, at least, we must understand. It is the ending built from the best tested law in all of science. So let us grant it. Let us walk into the long dark and watch the last star die. Because it is precisely there, in the ending physicists thought they understood best, that the strangest problems of all are waiting. Part 7. Suppose it simply fades. The idea that the universe might die quietly is older than the idea that it might die at all. It surfaced in the 1850s, in the era of steam, when physicists first understood engines deeply enough to notice that the universe is one. In 1852, William Thomson, later Lord Kelvin, published a short paper with an unassuming title about a universal tendency in nature toward the dissipation of energy. Energy, he had realized, is never destroyed, but it is constantly being degraded, sliding downhill from useful, concentrated forms into diffuse, lukewarm uselessness. A fire's heat spreads into the room and can never be gathered back to light the fire again. Hermann von Helmholtz drew the cosmic conclusion 2 years later. If the degradation is universal and one way, then the universe is spending an inheritance it can never replenish, and there will come a day when nothing is left to spend. In 1865, Rudolf Clausius gave the degradation its scientific name, entropy, and compressed the fate of everything into one sentence of imperial calm. The energy of the world is constant. The entropy of the world strives toward a maximum. The picture that grew from that sentence came to be called the heat death of the universe. Not death by fire, and not by ice exactly. Death by evenness. A universe where the temperature is the same everywhere is a universe where nothing can happen anymore. Modern cosmology filled in the schedule, and even a gentle sketch of it rearranges your sense of time. Stars are the universe's great spendthrifts, and they are a strictly limited edition. The raw material for making them, cold hydrogen gas, is finite, and galaxies are slowly working through the last of it. Star formation peaked billions of years ago. The universe's productive years, astonishingly, are already behind it. The brilliant heavyweight stars burn out first, in mere millions of years. Stars like our Sun last billions, then swell, shed their outer layers, and settle into white dwarfs, those Earth-sized cinders we met earlier, which do nothing but cool forever. The misers of the stellar economy are the red dwarfs, small, dim stars that sip their fuel so slowly they can shine for trillions of years. But trillions is not forever. In something like 100 trillion years, the last new star will have formed, and after that, one by one, the survivors gutter out. Beyond them stretch eras with almost nothing in them, dead remnants cooling toward the temperature of space, stellar corpses slowly scattered from their galaxies by chance encounters, and, on timescales measured in numbers with 100 zeros, even black holes evaporating, leaking their mass back into the darkness as a whisper-faint mist of radiation, until the largest of them are gone. Come and watch the very end of light, because it deserves a witness. It is roughly 100 trillion years from now, 7,000 times the current age of the universe, and in the darkness of the merged island galaxy, one star remains. It is a red dwarf, small and dim, and it has been burning with miserly patience since before most of the sky went dark. You drift in a slow orbit above it. Its glow is not the fierce yellow-white of our young sun, but a dark, tired crimson, the colour of the last coal in a hearth long after midnight. There is no drama in what happens next, and that is the heartbreaking part. The star does not explode. It is far too small for that. It simply runs out. Over unhurried ages, its light reddens further, and dims, and reddens, the way an ember does when you stop blowing on it, a fading you can only notice by looking away for an eon and looking back. At some point that no instrument could sharply define, the fusion in its core quietly stops, and the surface begins its long cooling, and the light fades below the threshold of any possible eye. There is no final flicker, no moment of extinction to timestamp. Darkness does not fall on the universe. It settles, the way silence settles on a house when the last conversation ends and no one notices which word was the last one spoken. What remains after the last star is not nothing, not yet. It is a universe of leftovers, black dwarfs, the fully cooled corpses of white dwarfs, neutron stars spinning ever more slowly, black holes patiently evaporating, thin gas, stray particles, and the ever-lengthening dark. And the direction of everything remains what Clausius said it was. Every remaining difference, every place slightly warmer than its surroundings, every clump slightly denser than the average, is a form of unspent wealth, and the universe spends it, transaction by transaction, toward perfect evenness. The endpoint is a cosmos at one uniform temperature, fractionally above absolute zero, where no energy can flow because there is no downhill left anywhere. Physicists describe it as equilibrium. It is a universe in which nothing distinguishable from anything else ever happens again. No light, no change, no events. Just the same cold stillness, cubic light year after cubic light year, forever. It is worth being precise about why evenness, rather than cold, is the true executioner. Because the distinction is the whole physics. Cold is not the enemy of activity. Difference is its fuel. A steamship does not cross the ocean because the ocean is warm. It crosses because the fire in its boiler is hotter than the water around it. And useful work lives in that gap. The 19th century physicists loved this image. Drop that same ship into an ocean of perfectly lukewarm water, with a boiler at exactly the ocean's temperature, and it does not matter how much heat energy surrounds it. trillions upon trillions of joules, all of it untouchable. No gap, no flow, no flow, no work, no work, no events. The heat-death universe is that lukewarm ocean, scaled to everything. Energy everywhere. All of it stranded, none of it able to move. Even the temperature floor is stranger than simple zero. If dark energy truly is the constant, the universe never quite reaches absolute zero. The horizon itself glows at a temperature of about 10 to the minus 30 Kelvin, a number so close to nothing that no thermometer could distinguish it. And yet, as we will see, just barely enough warmth to matter over infinite time. Hold that strange little detail. It is a loaded gun on the wall, and eternity will fire it. And here, at last, you might think, is an ending we truly understand. Notice how different it feels from everything else tonight. No knife-edge parameters, no shape-shifting energy fields, no singularities where the equations give up. Heat-death asks for no new physics at all. It is simply the second law of thermodynamics, the most battle-hardened law in all of science, allowed to finish its sentence. Arthur Eddington, the great astronomer of the early 20th century, once wrote that if your pet theory contradicts Maxwell's equations, so much the worse for Maxwell's equations. But if it contradicts the second law of thermodynamics, there is nothing for it but to collapse in deepest humiliation. That is the confidence behind the long fade. Of all the endings on the menu, this is the one built entirely from physics that has never lost. But before we accept it, look closely at what this ending actually is, because it hides a structural oddity that none of the other endings share. The Big Rip is an ending in the fullest sense. Time itself terminates at the singularity. There is no next page. The Big Crunch, likewise. The story closes. Heat-death is not like that. Nothing terminates. Time does not stop at equilibrium. The clock of the universe keeps ticking, uselessly, through the stillness. A stillness that simply continues, hour after empty hour, for infinity. Heat-death is not an ending at all. It is an infinite afterward. Everything interesting stops happening, and then the universe endures, without events, without change, forever. And infinity, it turns out, has fine print. To trust the long fade as the true ending, you have to trust one thing absolutely, that time's arrow, the one-way flow from ordered past to disordered future, holds firm all the way out, through numbers with 100 zeros, and far beyond, without a single exception, eternally. That seems safe. It is the deepest regularity in our experience. It is the reason you were younger yesterday. But here is what almost nobody outside physics knows, and what the second half of tonight's story is about. When physicists tried to prove that the arrow of time must point forward, tried to derive it from the fundamental laws, they failed. They are still failing, and the reasons they fail, discovered more than a century ago and never resolved, do something remarkable when you carry them into an eternal universe. They quietly begin to dismantle the very ending we just watched. The trouble started with a man, a deck of cards, and a firework that refuses to run backward. Part 8. The Arrow Nobody Can Derive. Picture a firework bursting over a dark river, the shell climbing, the bloom of sparks, the trails feathering outward and dying. Now run the film backward. Scattered embers rise from the water, converge with impossible coordination, gather themselves into a tight, bright knot, and swallow their own light as they retreat into an unexploded shell. You laugh, because it is obviously wrong. Nothing in your life has ever run that direction. But here is the fact that has haunted physics for a century and a half. Nothing in the fundamental laws forbids it. The equations governing every particle in that firework, their motions, their collisions, the forces between them, work identically in both directions. Play any microscopic process forward or backward, and both versions obey the laws of physics perfectly. At the level of atoms, there is no arrow, no forward, no backward, no preferred direction of time at all. And yet you have never once seen a firework unexplode. Why not? Why does time, in a universe whose laws do not care about direction, so ruthlessly pick one? The man who answered this, as much as it has ever been answered, was Ludwig Boltzmann, a Viennese physicist of the late 1800s. His insight was that the arrow of time is not written in the laws, it is written in the counting. Think of the universe the way a casino thinks of cards, and start with a brand new deck, every suit in order, every card in its place. Knock that deck off a table, gather the cards blindly, and ask what you are holding. There is exactly one arrangement that restores the factory order, and there are, this is the actual number, about 8 times 10 to the 67 other arrangements. That figure is so far beyond intuition, it needs an anchor. It is comparable to the number of atoms in the entire Milky Way galaxy. Shuffling a deck back into perfect order by chance is like reaching blind into the whole of our galaxy and pulling out the one atom you had marked. Nothing forbids it. The odds simply annihilate it. Now replace the cards with atoms. A hot cup of coffee in a cold room, a tidy arrangement of energy, is a fresh deck. There are relatively few ways for the energy to stay gathered in the cup, and an astronomical number of ways for it to be dispersed through the room. Every jostle of every molecule is a shuffle. So the coffee cools, the energy spreads, the ordered becomes disordered, not because any law commands it, but because disorder outnumbers order by margins that make 10 to the 67 look shy. Entropy, Clausius's quantity, is just this counting made rigorous. It measures how many microscopic shuffles look the same from outside. The second law of thermodynamics, the iron law behind heat death, turns out to be a statement of probability, not necessity. Entropy increases because entropy overwhelmingly tends to increase. The unexploding firework is not impossible. It is merely waiting on odds that dwarf the age of the universe. Time's arrow, in Boltzmann's picture, is what it feels like to live inside a deck that is still being shuffled. The English astronomer Arthur Eddington later gave the idea its permanent name, Time's arrow, and made its status plain. The direction of time is the direction in which the shuffling proceeds. Hold on to that deck of cards. It has one more appearance to make tonight, and its second appearance will undo its first. For our story, what matters is what this explanation quietly does to the end of the universe. Heat death, remember, leans its full weight on the second law. Differences dissipate, order degrades, evenness wins, forever. If the second law is fundamental, carved into reality, that lean is safe. But Boltzmann had just revealed that it is not carved anywhere. It is a tendency of shuffling, a statistical habit, an overwhelmingly reliable rule of thumb. The most secure ending on the menu is built not on bedrock but on odds. Very, very good odds. And an eternal universe, as we are about to see, is precisely the arena in which very good odds stop being good enough. The first blow landed almost immediately, and it came from inside the house. Josef Loschmidt was not Boltzmann's rival. He was his senior colleague, his mentor in some ways, and his friend, which perhaps made it worse when Loschmidt, in 1876, pointed out the crack at the base of the whole construction. Take any system marching dutifully toward disorder, he said, and imagine reversing the velocity of every single particle, every atom instantaneously sent backward along its own path. The laws of physics permit this reversed state without complaint, and that reversed system will retrace its history exactly, order increasing at every step, entropy falling, the shattered reassembling, the coffee reheating, the firework returning to its shell. For every microscopic history that increases entropy, there exists a perfectly legal mirror history that decreases it, exactly as many, one for one. So the counting alone cannot explain the arrow. If disordered futures so overwhelmingly outnumber ordered ones, the same counting applies in reverse. Ordered pasts are exactly as outnumbered. Run Boltzmann's logic backward and it predicts, with the same crushing confidence, that the past should also have been more disordered than the present, that memory, history, and the fresh deck itself should never have existed. The statistics, left to themselves, point both ways. The arrow does not come from the laws, and it does not come from the counting. It has to come from somewhere else. Where it comes from, as far as anyone can tell, is the beginning. The only way Boltzmann's explanation works is if the universe started in a state of almost inconceivable order, a freshly manufactured deck of cosmic scale, so that 14 billion years of shuffling have been unwinding that initial perfection ever since. Philosophers of physics call this the past hypothesis, and it is genuinely a hypothesis, an assumption, imported from outside the laws, that the Big Bang was staggeringly special. Roger Penrose once estimated just how special, by asking what fraction of possible starting configurations look like ours. Smooth, ordered, primed for structure. His answer, 1 part in 10, to the power of 10, to the power of 123. That denominator has more zeros than there are particles in the observable universe. There is no comparison that tames it. And no accepted principle of physics explains why the universe began in so absurdly improbable a state. The arrow of time, the fact that causes precede effects, that you remember yesterday and not tomorrow, that the universe runs down rather than up, rests, at bottom, on an unexplained stroke of cosmic luck. To say the universe will end in disorder, we must assume it began in order, and nobody knows why it did. You might wonder whether any of this can be tested, whether the reversibility hiding under the arrow is real physics or philosopher's smoke. It is real, and laboratories touch it. Since 1950, magnetic resonance physicists have known how to take trillions of atomic nuclei, each a tiny spinning magnet, let them drift out of step into apparent disorder, and then, with one precisely timed pulse, flip the entire ensemble so that every spin retraces its path and the original order re-emerges, seemingly from nowhere. It is Loschmidt's reversal made flesh, performed daily in hospital scanners and research labs. Modern versions do it with chains of trapped ions and clouds of ultra-cold atoms, and every such experiment reports the same two findings. The reversal genuinely works. Microscopic time symmetry is not a technicality. Disorder really can be marched backward, and the reversal is desperately fragile. The slightest uncontrolled nudge, a stray field, a wandering molecule, an imperfect pulse, and the retracing collapses, and the ordinary drift toward disorder resumes, as if it had never been challenged. The arrow, these experiments whisper, is not a wall. It is a tide, resistible in a teacup, for a moment, at enormous effort, and utterly irresistible at scale. Boltzmann himself did not live to see any vindication. His conviction that atoms were real, the very foundation of his statistical worldview, was scorned through his later years by influential colleagues who considered atoms a fiction of bookkeeping, and the objections of Loschmidt and others gnawed at the edifice he had built. He fought for decades, in print and in lecture halls, increasingly exhausted, increasingly alone. His life ended in despair in 1906 at a seaside resort near Trieste, 1 year, almost to the season, before new experiments on the jittering of particles in fluid began convincing the world that atoms were exactly as real as he had always insisted. On his gravestone in Vienna, above his name, is carved a single line of mathematics. S equals K log W. Entropy is the counting of arrangements. The equation that gave time its direction stands over the grave of a man who ran out of it, and who never learned that he had been right. And the deepest objection to his life's work was still on its way. It had been published, quietly, in a French mathematics journal, years before his death. A theorem, not about entropy at all, but about eternity. Carried to its conclusion, it says that in any universe that lasts forever, Boltzmann's shuffling deck does something no one was prepared for. It comes back. Part 9. Eternity's theorem. In 1890, the French mathematician Henri Poincaré published a paper on, of all things, the gravitational dance of three bodies, a study written for a prize offered by the King of Sweden, and famous partly because Poincaré found a subtle error in his own winning entry and paid more than the prize money to have the corrected version printed. Buried inside that paper was a theorem that had nothing to do with prizes and everything to do with eternity, and it says this: take any system that is finite, finite matter, finite energy, confined possibilities, and let it evolve under laws that can, in principle, run either direction. Wait long enough, and the system must return arbitrarily close to any configuration it has ever been in. Not may, must. Every arrangement the system has ever passed through, it will pass through again, and again, and again, endlessly, if the waiting is endless. The logic, stripped of its machinery, is almost embarrassingly simple. A finite system is a deck with a finite number of possible hands. Deal forever, and you cannot produce novelty forever. Eventually, the same hands come around. There is no destiny in it, no design, no cosmic nostalgia, only arithmetic. Finite possibilities divided by infinite time equals repetition. Physicists call it Poincaré recurrence, and it is not a speculation or an interpretation. It is a proved theorem of mechanics, as solid as anything in the subject. 6 years later, a young German mathematician named Ernst Zermelo, then an assistant in Berlin, later famous for laying the foundations of set theory, picked up Poincaré's theorem and aimed it directly at Boltzmann. If every configuration recurs, Zermelo argued, then entropy cannot increase forever. Wait long enough, and the universe must revisit states of lower entropy. Must, by theorem. The shuffled deck must eventually deal itself back into factory order. The cooled coffee must someday reheat. The second law, over infinite time, cannot be a law at all. At best, it describes one long upswing between recurrences. Boltzmann's reply was characteristically practical. He calculated how long you would actually wait. For even a thimbleful of gas, a modest trillion atoms, the recurrence time comes out around 10 to the power of 10 to the power of 19 seconds. That is not a number with 19 zeros. It is a number whose count of zeros has 19 zeros. Boltzmann's point was blunt. The theorem is true, and it does not matter. You should be prepared to wait, he said, that long. And for every practical purpose, in the history of practical purposes, he was right. But the end of the universe is not a practical purpose. Heat death, remember, is not an ending, but an infinite afterward. And against infinity, Boltzmann's defense evaporates, because infinity is the one opponent that is always prepared to wait. Modern physicists have redone his calculation at full cosmic scale. In 2002, 3 theorists, in a paper frankly titled Disturbing Implications of a Cosmological Constant, estimated the recurrence time for a universe like ours at around e to the power of 10 to the power of 122. The physicist Don Page once worked out a related figure, often described as the longest finite time ever printed in a physics journal. 10 to the power of 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 2.08, a tower of exponents so tall that it makes no measurable difference whether you count it in seconds, years, or lifetimes of the universe. These numbers are not predictions to circle on a calendar. They are the mathematical way of saying unimaginably far, but not never. And an eternal universe has no appointment book. It has only forever, and forever absorbs any finite number, however grotesque, as if it were nothing at all. If the universe is finite in its possibilities and infinite in its patience, then the long dark after the last star is not a final state. It is an intermission, the longest intermission arithmetic can describe, after which the stage, by theorem, refills. The strangest part of this idea's history is that physics was not the first to arrive at it. A prisoner beat the mathematicians by 19 years. It is the autumn of 1871, and the sea fortress of Fort du Toureau sits on its rock off the coast of Brittany like a stone ship at permanent anchor. The tide slams the same walls in the same rhythm it has kept for 2 centuries. Inside, in a cell that owns 1 window's worth of grey Atlantic light, sits a thin man of 66, with white hair and the stillness of someone who has done a great deal of waiting. His name is Louis Auguste Blanqui, and he is, by official reckoning, the most dangerous man in France. A professional revolutionary who has spent more than half his adult life in prisons, who has been sentenced to death and reprieved, who has led risings against kings and emperors and lost every single one. The government fears him so specifically that it is holding him here, the fortress's sole prisoner, garrisoned by dozens of soldiers, while Paris burns through the aftermath of the Commune, an uprising that begged, futilely, to trade all its hostages for this one old man. The head of the French government refused, reportedly reckoning Blanqui alone was worth an army corps. Denied newspapers, denied visitors, denied the revolution that was the only life he knew. Blanqui asks his jailers for paper and for books about the stars. Night after night, by candlelight, with the waves keeping their metronome against the walls, he writes, not about politics, about the universe. And the little book that grows under his hands, published the following year under the title Eternity by the Stars, contains an argument that no scientist had yet dared to state so plainly. The argument runs like this. The universe, Blanqui reasons, is built from a finite catalogue of ingredients, 100-odd elements, so many particles, only so many ways to combine them. But space, he believes, is infinite, and time has no end. Finite combinations, infinite trials. Therefore, and he follows the arithmetic without flinching, every possible arrangement of matter must occur, and must occur again, endlessly. Every world must repeat. Every life must repeat, atom for atom, choice for choice. Somewhere in eternity's ledger, this exact cell, this exact candle, this exact tired hand moving across this exact page, recurs without limit. He writes it down in a sentence that still stops the breath, a century and a half later. What I write at this moment, in a cell of the Fort du Toureau, I have written and shall write throughout all eternity. At a table, with a pen, in circumstances wholly alike. The universe, he concludes, is a theatre with a finite repertoire, restaging the same performances forever. There is horror in it, his defeats too recur forever, and a strange consolation, the only immortality arithmetic will grant an atheist revolutionary. Nothing that exists is ever truly lost. History does not remember the book kindly, or at all, for decades. It sells almost nothing, and Blanqui dies a decade later, having spent, by the final count, some 33 years of his life behind bars. Only much later do readers rediscover the little volume and recognize, in the ravings of the locked-up man, a rigorous anticipation of a theorem Poincaré would prove from mechanics in 1890, and cosmologists would recompute from quantum theory in 2002. Eternity, given finitude, is a wheel. 11 years after Blanqui's cell, and in apparent ignorance of him, Friedrich Nietzsche arrived at the same wheel from philosophy and asked what it does to a human soul. He framed it as a test. Imagine, he wrote, a demon stealing into your loneliest loneliness to tell you that this life, exactly as you have lived it, you will live again, innumerable times, with nothing new in it, every pain and every joy returning in the same sequence, down to this spider, this moonlight, this moment. Would the thought crush you? He asked. Or has there ever been an instant so complete that you would bless the demon for the news? Nietzsche called the idea the eternal recurrence, and considered it the heaviest weight a mind could lift. Notice who has now arrived at the same conclusion by three separate roads: a prisoner from arithmetic, a philosopher from psychology, a mathematician from mechanics, and, a century on, cosmologists from the equations of an eternal universe. Ideas that important have a way of being discovered by everyone, and it is worth hearing, just for a moment, how strange this wheel sounds against the oldest human pictures of time, because most of them insisted on the opposite. The traditions of endings are endings with meaning, a last day, a final accounting, a scroll rolled up. The moment, promised in the book of Revelation, when an angel plants 1 foot on the sea and 1 on the land, and swears that time shall be no longer. Michelangelo spent 4 years painting that finality across the altar wall of the Sistine Chapel. The dead rising once, judged once, everything weighed exactly 1 time, because everything happens exactly 1 time. Cyclic traditions exist, of course. The great turning ages of Hindu cosmology run closer to Blanky's wheel than anything in the West. But even they close their cycles with renewal, with meaning carried across. What no tradition imagined is the version the arithmetic actually delivers: repetition, without memory, without judgment, without progress, the same performances, restaged forever, for an empty house. Endings, it turns out, are what give time its moral weight, and an eternal universe, examined closely, has trouble keeping any. So the calmest ending on the menu now looks like this: an infinite stillness that must, by theorem, occasionally stir, restaging, at intervals too large for notation, anything it has ever contained. But even that is not the deepest trouble, because so far we have only asked what recurs. The truly unsettling question, the one that turned this entire subject radioactive inside modern cosmology, is who. In an eternal universe, the things most likely to flicker back out of the dark are not stars and not worlds. They are minds, and counting them almost breaks physics. Part 10. The Observers in the Noise. The idea began, fittingly, with Boltzmann himself, as a rescue attempt. In 1895, pressed by the objections we have been following, he floated a remarkable proposal in a letter to the journal Nature, crediting the germ of it to his old assistant, a man he called simply Old Schutz. Perhaps, Boltzmann suggested, the universe as a whole already sits at equilibrium, already dead, already even, and has for eternity. But in an eternal equilibrium, fluctuations happen, chance ripples of order, local and temporary, like a shuffled deck momentarily dealing 3 aces in a row. Given infinite time, he reasoned, even an enormous fluctuation must eventually occur, a ripple large enough to look like an entire ordered universe, with hot stars and cold sky and entropy low enough to have somewhere to climb. Our whole cosmos, in this picture, is a rare statistical shiver in an infinite dead calm. And why do we happen to live inside so absurd a rarity? Because, Boltzmann answered, nothing lives anywhere else. The dead calm has no witnesses. Only inside the fluctuations can anyone be around to ask why the world looks so improbably fresh. It was, and remains, one of the most audacious ideas anyone has proposed about existence. The universe as a lucky deal in an eternal casino, observed only because luck is the only place observers can stand. For a while, it even seemed to work. Then someone did the counting, and the counting is merciless. Fluctuations come in sizes, and small ones are not just more common than large ones. They are more common by exponential factors that beg a description. A ripple that assembles 1 galaxy is unimaginably cheaper than one that assembles 100 billion. A ripple that assembles 1 star system is unimaginably cheaper than that. Follow the gradient all the way down, and you reach the cheapest possible witness: a single mind. 1 brain, assembled by chance for 1 moment, complete, warm, firing, with memories already in place, Memories of a childhood that never happened, an education never received, a universe never actually seen. Everything you are experiencing right now, this room, this voice, the feeling of a long story unfolding, is, physically speaking, a pattern in one brain that a sufficiently obliging fluctuation could produce directly, without bothering to build the 14 billion years of history the memories describe. Physicists came to call such an entity a Boltzmann brain, in honor of the man whose rescue attempt accidentally predicted it, and the modern name was pinned on in 2004, in a paper by Andreas Albrecht and Lorenzo Sorbo. The numbers attached to it are the strangest in this entire strange story. In an eternal universe resting at that faint horizon temperature we flagged earlier, 10 to the minus 30 degrees above nothing, a fluctuation producing a functioning brain is estimated to occur perhaps once every 10 to the power of 10 to the power of 70 years. Written down, that frequency is indistinguishable from never. Against eternity, it is a drumbeat. So come out into it, one last time, the equilibrium dark, unimaginably far downstream of the last star. Nothing has happened here, by any ordinary meaning of happened, for spans of time that no tower of exponents can make vivid. But the quantum fields that fill all of space have never quite gone silent. They ripple, faintly, the way a sea ripples under no wind at all. Watch long enough, and eternity does nothing but watch, and the ripples occasionally align. A few particles, a knot of warmth, gone. Somewhere else, eventually, a molecule, and once in 10 to the 10 to the 70 years, the alignment runs deeper, and for a moment, there drifts in the darkness a thing that thinks. It arrives mid-thought. It remembers a life, a childhood, a favorite room, a voice it loved, none of which ever occurred. Perhaps it has a moment of something like wonder, and then the fields relax, as fields do, and it is gone, and the calm closes over the place where it was, and the intermission resumes, as though nothing at all had interrupted it. No harm has been done. Nothing was lost that was ever really there. But eternity keeps its own books, and in those books, given literally infinite time, entries like this one do not stop accumulating. And here is where the deck of cards makes its promised return, and takes back everything it gave. Boltzmann's shuffle explained the arrow of time. One perfect order, 10 to the 67 disorders, so the deck only ever slides downhill, and time flows. That was the deck's first lesson, but deal forever, and an eternal universe deals forever, and the same counting inverts. Every hand recurs. The perfect order comes back, the three aces come back, and hands you never imagined, hands that remember being dealt when they were not, come back more often than the honest ones. The image that explained why time flows forward is the very image that, stretched over eternity, dissolves the flow into noise. The casino always wins in the short run. In the infinite run, the casino produces everything, including gamblers who never walked in. Now, the reasonable response to all this is a slightly exasperated question. Why do serious scientists care? No one will ever meet a Boltzmann brain. The timescales are beyond parody. Here is why they care, and it is worth following closely, because it may be the strangest twist in tonight's story. The trouble is not that these fluctuated minds might exist someday. The trouble is what their statistics do to us, here, now. If the universe endures forever, then over its whole history, minds assembled by fluctuation vastly outnumber minds assembled the slow way, by stars and planets, and billions of years of evolution. Not by a little, by those tower of exponents margins. Which means that if you select a mind at random from eternity's full ledger, any mind holding memories exactly like yours, the overwhelming majority of them are momentary flickers whose memories are false. Follow the statistics with a straight face, and you reach an absurd conclusion. You should bet that you are one of them, and that the experiments, the telescopes, the supernovae, the entire evidentiary basis for the theory itself, exist only as false memories in a transient cluster of particles. And there the whole structure eats its own foundation, because a theory that concludes its own evidence is probably hallucinated has sawed off the branch it sits on. The cosmologist Sean Carroll has given this failure a precise name. Such theories are cognitively unstable. They cannot be believed consistently because believing them undermines every reason for believing them. Let this be said clearly and gently because it matters. No one has proved you are a fluctuation, and no serious physicist claims it. You are not being asked, tonight, to doubt your own childhood. The argument runs the other way, and it is used the other way. Because the conclusion is intolerable, the premise must be suspect. And so the Boltzmann brain has become something no thought experiment quite was before. A quality control test for entire universes. Cosmologists now routinely check candidate models of dark energy, of inflation, of the far future, by asking whether they overproduce fluctuated observers, and models that do are marked down, not for disagreeing with any measurement, but for making the reasoner statistically impossible. The physicist Don Page pushed the logic to its most concrete conclusion. Perhaps our universe simply must not last forever. Perhaps the vacuum of space is required, on pain of absurdity, to be unstable, scheduled to decay on some immense but finite timescale, precisely so that eternity never gets its infinite deals. Sit with how remarkable that is. A hypothetical mind, flickering in a darkness no one will ever visit, is being used as evidence about how long the universe is allowed to live. The study of the end of the universe has looped back and seized the student. We set out to ask when everything ends, and the mathematics turned the question around and asked whether the asker can trust the asking. One more door deserves a brief, careful glance before we leave this hall of mirrors, because it points the same direction. In one reading of quantum mechanics, the many worlds interpretation, every quantum event splits reality into branches, and everything that can happen does happen, somewhere in the branching. Some thinkers, most famously the physicist Max Tegmark, have explored a thought experiment nicknamed quantum suicide, which seems to imply that a conscious observer would only ever experience the branches in which they survive, and taken to its limit, that from the inside, experience simply never ends. Be clear about its status. It is a thought experiment, not a result. It depends on an interpretation that remains unproven. Tegmark himself has argued that real death is gradual, rather than a clean quantum coin flip, and that the immortality conclusion likely fails, and no experiment has ever shown that consciousness follows surviving branches. It has no claim on your beliefs. It belongs in tonight's story for exactly one reason. It is yet another case, we have now collected several, where the question "does everything end?" turned out to hinge not on telescopes, but on the unresolved foundations of physics itself. What began as astronomy keeps ending up as philosophy with equations. And all of it, the recurrences, the fluctuations, the counting of observers, still rests on one final assumption, the deepest one of all, so ingrained we have not even thought to question it tonight. We have assumed, from the first sentence, that time flows, that there is a current, carrying the universe from a beginning toward an ending, with us adrift in the middle. The physicists who work at the very foundations, on the equations that would unite gravity with the quantum, are not at all sure that is true. And if it is not, then the question of when time ends does not get a new answer. It stops being a question. That is where we go next, and it is the strangest room in the house. Part 11. Maybe time cannot end, because it never flowed. Everything tonight has leaned on a picture so natural you have never had to think of it as a picture, time as a river. The universe is carried along in the current, from the headwaters of the Big Bang toward some distant mouth, a rip, a crunch, an endless delta of fading warmth. Asking how the universe ends is asking what happens at the end of the river. But the physics of the last 100 years, read carefully, keeps suggesting something that sounds absurd and refuses to go away. There may be no current. The river may be frozen, not stopped, but complete. Every bend and eddy existing at once, with flow being something we feel, rather than something the universe does. The suggestion begins with Einstein, not with his cosmology, but with what his relativity does to the word now. In our ordinary picture, now is a universal blade, a single present moment slicing across all of reality, with everything on one side already gone, and everything on the other side yet to come. Relativity showed, with the full force of experiment behind it, that no such blade exists. Observers moving differently slice the universe into past and future differently, and no slicing is more correct than any other. Two people passing on the street, one walking toward a distant galaxy and one away, are entitled to disagree, legitimately, physically, about what is happening there right now, and their disagreement can span centuries. The conclusion, resisted at first even by physicists, is that reality cannot be a three-dimensional scene being repainted moment by moment. It is a four-dimensional structure. Physicists call it the block universe, in which all events, past, present, and future, simply exist, the way all the frames of a film exist in the canister at once. The film does not flow, the film merely is. And in a block universe, this changes what an ending can be. The end of the universe is not approaching, the way a waterfall approaches a boat. It is a feature of the block, a far edge or no edge, exactly as real and exactly as motionless as the Big Bang or as this evening. Endings do not happen, they sit. Einstein did not treat this as wordplay, and one letter shows how completely he meant it. In March of 1955, his oldest friend died, Michiel Besso, the engineer who had been his sounding board since their patent office days in Bern, the only person thanked in the 1905 paper that created relativity. Einstein, too ill to travel, wrote to Besso's family, and in the letter, he said something that has been quoted at physics funerals ever since. Now he has departed from this strange world, a little ahead of me, Einstein wrote. That signifies nothing. For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. It is worth hearing that sentence as he meant it, not as poetry, and not as a soft consolation reached for in grief. He was stating plainly what he believed his own equations say about the deaths in the room, including the one he knew was coming for him. In the block, Besso's life is not erased. It is there, complete, at its own coordinates, as permanent as any galaxy. Einstein died 4 weeks later, still holding that view of what his friend's ending, and his own, actually was. Whatever else the block universe is, it has been believed, all the way down, by the person who best understood where it came from. But relativity was only the first push. The second came from the attempt to write down the deepest equation in physics, and it produced the strangest artifact in this whole story. In 1965, John Wheeler, the physicist who popularized the term black hole, had a layover between flights at the Raleigh-Durham Airport in North Carolina, and rather than waste it, he summoned a colleague, Bryce DeWitt, to meet him there. Sitting in the terminal, working between departure announcements, the two men assembled something physicists had circled for decades, an equation applying quantum mechanics not to a particle or an atom, but to the universe as a whole, a wave equation for everything. DeWitt worked it into publishable form in 1967, and it has been known ever since as the Wheeler-DeWitt equation. It is a candidate for the most fundamental equation ever written, and it has a property that no one ordered and no one has ever fully digested. It contains no time. In every ordinary equation of physics, time is the lead actor. Things change as time passes. That is what an equation of motion means. In the Wheeler-DeWitt equation, the symbol simply is not there. Read literally. It says the quantum state of the universe as a whole does not evolve. Nothing happens. The totality does not move, does not change, does not flow. It simply is, the whole block, held in a single timeless expression. DeWitt himself was never comfortable with it. He called it, in later years, that damned equation. Physicists call the discomfort by a politer name, the problem of time, and it remains, 60 years on, an open wound at the exact point where our two deepest theories meet. When gravity and the quantum are forced to speak to each other, the first casualty of the conversation is time. Faced with an equation that deleted time, physicists split into camps, and the camps map every option left on the table. The first camp says, time is not fundamental, but it is not fake. It emerges from within. In 1983, Don Page, the same Don Page we met vetoing eternities, and William Wooters, showed something lovely. Even in a perfectly frozen total universe, one piece of the universe can serve as a clock for the rest. If the pieces are quantum entangled, then relative to the reading on one piece, the other pieces change. From outside, nothing happens. From inside, history unfolds. Time, in this picture, is not a river the universe floats in. It is a relationship between the universe's parts, evolution without evolution, as their title put it. Decades later, in 2013, a team in Italy built a toy demonstration with a pair of entangled photons. Measured from outside, the pair's joint state sat perfectly still. Measured from inside, using one photon as the clock, the other photon ticked. A frozen hole with moving parts. A universe in miniature, doing exactly what Page and Wooters said it could. The second camp is more radical. The British physicist Julian Barbour has spent a career arguing that time does not exist at all, not fundamentally, not emergently, not at any level. What exists, Barbour proposes, is an immense landscape of configurations, frozen arrangements of everything, each one a complete three-dimensional now. Nothing connects them. Nothing flows between them. They do not occur in an order. They simply are, all of them, timelessly, like pages of a book that was never meant to be read in sequence. Why then does this moment feel like part of a story? Because, Barbour answers, some nows contain records, memories in brains, photographs in drawers, fossils in rock, light en route from dead stars, and a now that contains records feels like it has a past, whether or not any past ever ran. Your memories of this morning are, right now, a configuration of your neurons. That much is plain neuroscience. Barbour simply asks the question no one wants. What, beyond those present tense records, does the pastness of the past actually consist of? He titled his major book The End of Time, and the title is a quiet joke with a sting in it. Time cannot end, because time never began. There is no river to run dry. There are only the still pages, and among them, pages like this one, pages that carry the feeling of a story in motion. The third camp, associated with the Italian physicist Carlo Rovelli, threads between them with an analogy of unreasonable power. Consider temperature. A single molecule has no temperature. The concept simply does not apply. Temperature is a statistical summary, something that emerges only when trillions of molecules are described together, in blur. No one is troubled by this. No one demands to know where the temperature of one molecule went. Now, Rovelli proposes, hold time the same way. A single quantum event may have no time, no before, no after, no flow. Time, like temperature, may be what the world looks like from far enough back, a coarse-grained summary of countless timeless events, real at our scale, absent at the bottom. Your own body runs on the same logic. A single cell does not have a heartbeat. The beating emerges when billions of cells act together, and it is perfectly real, and it is nowhere in the parts. If time is like that, real in the blur, absent in the grain, then asking whether time ends is like asking whether temperature ends, or where the heartbeat of one cell goes when you die. The question is not wrong. It is not even wrong. It dissolves, the way what is north of the North Pole dissolves. Not because the universe is hiding the answer, but because the words stop referring to anything once you leave the scale where they were coined. Stand back, now, and see what has happened to the question we have carried all night. We began by asking which ending the universe will meet, and we could not settle it. We asked whether the endings could even stay endings against eternity, and the theorem said no. And now, the deepest equations we possess have put the final piece on the table, the very frame of the question. Time, flowing, toward, may be a feature of us, rather than of the universe. This is the last and fullest sense of tonight's title. Physics did not merely fail to find the end of time. Physics, studying the end of time as hard as anything has ever been studied, arrived at the possibility that there is no such thing as time to end, that the river was always a picture, painted by creatures who remember in one direction, onto a reality that never flowed anywhere at all. The question did not get harder. It got stranger, so strange that we can no longer be certain it is a question. And that, 70 years of equations later, is where the honest trail actually ends, which leaves only one thing to do. It is time to answer the question we promised at the very beginning. With everything we now know, and everything we now know we do not. Part 12. What we actually know. So, how will the universe end? You were promised an answer tonight, and here it is. The complete, honest answer. The one the evidence will actually support, delivered without flinching. If dark energy is Einstein's constant, the universe ends in the long fade, the last star in about 100 trillion years, then the slow evaporation of everything, then the even dark, an ending that eternity itself may quietly unravel. If dark energy is phantom, the universe ends in the rip, on a real calendar date, perhaps a few tens of billions of years out. If dark energy is truly weakening, as the sharpest map we have keeps hinting, the universe may end in the crunch, the fall back into fire that the 20th century buried and the 21st has exhumed. And if the timeless physicists are right, the universe does not end at all, not because it lasts forever, but because ending is not a thing the universe does. It is a thing stories do, and the universe may not be a story. Every one of those answers is live. Not one of them is established. That is not a failure to report. After a century of the finest measurements our species has ever made, that plurality is the report. But say what is solid too, because the ground under this uncertainty is firmer than almost anything humans know. The universe is expanding, certain. The expansion is accelerating, certain, tested for a quarter century, crowned with a Nobel Prize. The census, 5% matter we understand, 95% we do not, measured to exquisite precision. The theorems about recurrence, the statistics of fluctuations, the timelessness lurking in the deepest equations, real mathematics, checked and rechecked. Even the disagreements are precise, quantified in sigmas, bounded by error bars, argued in public with the data on the table. This is not a subject in chaos. It is a subject in honest, rigorous, magnificent uncertainty, which is a different thing entirely, and a rarer one. And the story is not paused, it is accelerating, in every sense. Within the coming decade, the full 5-year DESI map will be complete. The Euclid Space Telescope will have charted billions of galaxies across a third of the sky, and new survey observatories will be photographing the entire visible heavens every few nights, catching thousands of fresh supernovae a year. The knife edge of Well may finally resolve. The evolving energy signal will either harden toward discovery or dissolve back into the statistical fog, and either outcome will be momentous. If it hardens, humanity will have watched the fundamental character of empty space change within a single generation of instruments. If it dissolves, we will be left holding a constant that no theory can explain, balanced forever on the one value where the future flips. Some of the people who will settle this are in graduate school right now. Some are children. The question of how everything ends is, at this moment, one of the most alive questions on Earth. And now name the pattern, because you have watched it all night, and it deserves to be said in one breath. In 1930, the end of the universe was one number, a density. Measure it, and know. By 2000, it was one substance, dark energy. Identify it, and know. By 2025, it was one derivative, the drift in a parameter called W, and the finest instrument ever aimed at it returned an answer that reopened endings instead of closing them. And beneath the instruments, all along, the question was quietly resting on two assumptions almost nobody thought to check: that time's arrow holds forever, which cannot be derived, and that time itself flows, which cannot be confirmed. Each generation attacked the question with better tools than the last. Each generation's tools worked, and each generation ended up holding a bigger question than the one it inherited. The sharper the map, the stranger the territory. That has been the law of this subject for 100 years, and there is no sign it is done being the law. So the more scientists study the end of the universe, the less they understand it. You have now seen exactly how that sentence works, and you can see it is not an insult to science. It is nearly the opposite. Fake questions shrink when you study them. They are small, and study exhausts them. Real questions grow. The end of the universe has grown under every instrument ever pointed at it. From a bookkeeping exercise into a puzzle about dark energy. From a puzzle about dark energy into a confrontation with eternity. From a confrontation with eternity into an open question about whether time is real. Only something with real depth behaves that way. The growing strangeness is the surest evidence we have that we are digging in true ground, that the universe is not a small thing pretending to be large, but a large thing we have barely begun to be honest about. There are really only two possibilities, and both are wonderful. Either the ending will someday be understood by minds that will look back on tonight's confusion with affection, or the universe is deeper than understanding, and there will always be another layer of strangeness to reward whoever looks next. Either way, the looking has been the best thing our species does. And so we are not waiting for the end. We are waiting to learn what kind of thing an ending is. That is the true answer to tonight's question. The one every measurement, every theorem, and every timeless equation has been pointing at all along. An event with a date, like the rip, a limit, approached forever, like the fade. A statistical mirage, dissolving and reforming, like the fluctuations in eternity's ledger. A place in a block that never moved. Nobody knows. Nobody has ever known. And you now understand the question better than the confident textbooks of a century ago ever did, because you know where its bottom drops away. Whatever an ending is, it is not near. Hold the scales one last time, gently. The universe is 13.8 billion years old, and the earliest ending on any serious table sits tens of billions of years out, several times the age of everything that has ever happened. The last star is 100 trillion years away. The strange arithmetic of recurrence lives beyond towers of exponents no calendar will ever hold. Tonight, every star that has ever shone on any human life is still burning. The sky over your roof is the same sky the first astronomers read, still crowded with light, still early. You live in the universe's brilliant morning, so early in the story that the story's own ending cannot yet be read even by the finest instruments on Earth. Whatever the ending turns out to be, the fade, the fall, the tearing, the page in a block, or something no one has imagined yet, it is farther from this quiet moment than any distance you have ever crossed, and no part of it is your concern tonight. So let the question rest where a century of brilliance has left it. Open. The dark between the stars is not counting down. The deck is still being shuffled. The island of light is still whole. The river of time, if it is a river, still runs strong past your window. Somewhere out there, at the bottom of the night, The universe is keeping its last secret, the way it has kept every secret worth having, patiently, beautifully, just beyond the edge of the sharpest map. Let it keep the secret a while longer. Close your eyes. The end of the universe, whatever it is, will still be unknowable in the morning, and the morning, unlike the ending, is certain to come.